Because if you click on the more dot dot dot, you can hide the panel. You want to check hide
Hide video
hide
panel.
and floating panel.
Oh, here.
And then also you can hide the video. So actually, if you escape, if you press escape, it will go back. Let's hide both. So if you go back to the more, let's first hide the video panel. And now let's hide the.
Oh, okay, okay. Okay, okay, that's good. Yeah, that's
We have
good.
a lot of folks on the, I think, shows us.
Okay.
Okay, so do you start recording?
Yeah.
Perfect. So welcome everyone to another colloquium in the Northwest Database Society series. Today we have Jianguo Wang from Purdue University. So Jianguo received his PhD from the University of California, San Diego. He worked with Yannis Papakonstantinou, and I think he knows how to pronounce his name, which is
Yeah, that's right. Yeah.
which is good. Then he worked for a while at Amazon, then at a startup company, and then he joined Purdue, where he is an assistant professor. He works on a hot topic, which are vector databases. So Jianguo, please take it away.
Thank you. Thank you very much. I mean, happy to be here. So I will share some progress about the vector databases that we have been working on. So just like a little bit of background about me. So I'm currently an assistant professor at Purdue. So before that, I spent some time in industry working on the Milvus vector database and the Amazon Aurora cloud native database. And then I did my PhD at UC San Diego, and in my research area is mainly about databases for the cloud and large language models, especially about disaggregated databases and vector databases. So for the disaggregated databases, we do both storage disaggregation and memory disaggregation, because in the cloud, all the resources they are separated, they are decoupled from each other. So basically, like how to redesign databases for the new disaggregated resources. Currently, like we are also working on disaggregated databases for data lakes. Okay. And then for vector databases, we are, doing, different, a variety of topics. From specialized vector databases to integrated vector databases. And also, like we do, like we solve how to improve the cost efficiency and auto tuning in vector databases. So in this talk, I will mainly focus on the integrated vector databases, about like how to support vector search inside existing databases, including relational databases and graph databases. If there's time, like I will talk something about multi-model databases that go beyond the current vector databases. Okay. Okay. And then so vector databases, like that's a very hot topic now. There are many different types of vector databases. For example, like a Pancall, Milvus, Face, or something. And also, like all the major relational databases, they have all supported vector search. For example, like Oracle, SQL Server, Postgres, MySQL, or something. So basically, all the major relational databases, they have all supported vector search. Well, like we started working on this area like pretty early, like even before large language models become popular. So we published the Milvus vector database paper in 2021, and then, but at that time, so vector databases were not very popular. There were only a few of them, and then like mostly they were about vector search libraries. So the motivation for vector databases at that time was about vector embedding. Because so basically you have a lot of unstructured data, like text, like you have images, you have videos, and then those kind of data, they can be turned into vectors. Now you can do advanced data analytics like product recommendation or image search over in a vector space. And that's something known as vector embedding. So that was the motivation at that time. But now, so the motivation is changed to large language models, because it turns out vector databases can address many critical limitations. In large language models, for example, hallucination, lacking domain-specific knowledge, or lacking up-to-date information. So basically, you can store those information in the vector databases, and then once you have a query, so you can search vector databases for relevant context, and then you can send the original query and also those relevant contexts as an enhanced augmented prompt to the large language model, now like you can get more accurate results. That's something known as RAG, retrieval augmented generation. So and then like only from that time, around like 2023, so vector databases suddenly become very, very hot. Okay. Well, there are two types of vector databases. One is specialized vector databases. So basically, you build a vector, databases from scratch. So those systems, for example, Milvus, Pinecone. So basically, they are designed explicitly to manage vector data. Well, another type of vector databases, they're about integrated vector databases. So basically, we want to build a vector search inside existing databases. Well, mostly about within relational databases, but basically all the many existing databases they have supported vector search. So that's the integrated vector databases. So in this talk, I will focus more about on the second category, because we find out for the specialized vector databases, there are many problems. For example, data silos or data redundancy or something, or extra extra lasting cost or something. So basically those kind of problems, they are also applicable to other specialized data models like graph data models or something. But here for vector databases, there are two unique problems. One is it's very hard to link the vector embeddings with their source data, because those kind of source data, they are usually they are stored in other systems. Now if you have a specialized vector database, now it's so the source data and their embeddings, they are somehow disconnected. So that will create a lot of consistency problems. So another one is in vector databases. We don't just do pure vector search. We also do something about advanced vector search. So basically, you don't want to you want to search. Not just about the vector data, and then you also want to search non-vector data. So some filtered, if you have some filters, and then you want to do some filtered vector search, and then it's pretty hard to support those advanced vector search inside specialized vector databases. So that's why the integrated vector databases, they are pretty popular, especially in industry. Well, there are also challenges for integrated vector databases. So one thing is performance, because vector data was now their first priority in existing databases. So is it possible to achieve high performance comparable to specialized vector databases, right? So that's one big issue. Another one is how to basically it's about high interoperability. So basically we want if we want to introduce a vector search inside the existing systems, we want to make it compatible with existing SQL semantics. Okay, with filters, with joins or something, and then we also want to support a hybrid vector search efficiently. So basically we want to solve these two challenges. And then I will use two examples to explain how to support vector search into existing databases. One is about relational databases, and then another one is about graph databases. For the relational databases, we have a collaborative work with single store. About how to implement a vector search inside the single store. Single store, that's a relational distributed relational database system in San Francisco. Well, they also have office here, and then so we build. We call the system a single store V. So basically, so the main idea is that we store the vectors as a new column, and then in this table, and then once we have this new vector column, then we build additional vector index on this particular column. So it's very similar to B tree over other columns. But the point is in this way, we can directly link the vector data with their source data, because they can also they can be stored in the same table. right? And also like it's very easy to support advanced vector search because like we have all the necessary data here. So that's the main idea. Well, like this kind of main idea is also applicable to other relational databases like Postgres or Oracle SQL Server or something. They are all like using this way. But the point is, for single store has some unique architectural benefits that I can make vector search to be more efficient. So like the first unique architectural benefit is something about, they're using LSM-based storage engine instead of B-tree-based storage engine. For the LSM-based storage engine, that means, so like there are, well, for the LSM, it's basically about the LSM tree. So basically like there are two parts. One is the LSM like has two parts. One is the in-memory part. Another one is the on-disk part. For now, like you don't have to, you can ignore like a row store or column store or something because for vector databases, we find that vector store, column store or row store, like they are not that matter much in terms of the performance of vector search. So you can just consider like in-memory part versus on-disk part. But the point here is for the in-memory part, that's mutable. Mutable, that means if you have some new data, those kind of new data will go to the in-memory segments first. And then if they are full, they are going to be, flushed to disk as immutable segments. So all the segments on disk, they are immutable. All the, segments, they are in memory, they are mutable, right? And now like we don't, for the in-memory part, we don't build any vector indexes. We just do full table scan because the in-memory part is usually small. And another point is so the in-memory part is always changing, right? And also like even if we build a vector index for the in-memory data, and then because the vector index is very slow in terms of updates, that means like it's not going to be very fast. So basically, like we just like don't build any in-memory index, and then like we only build a vector index for the on-disk segments, because well like for the on-disk segments, because like they are immutable, and then like this kind of immutability will have a lot of advantages for vector search. One thing is because like every segment like they are immutable, that means we don't have to consider updates. For this, if we build an index for this segment, because this segment is not going to be changed. There, later on, like they can be merged, they can be compacted to be a bigger one. But for that particular one, it's not going to be modified. So that means like we don't have to consider updates. That's very update friendly for vector indexes, right? And also like that means like because we don't have to consider updates, that means we can use any high performance vector index, right? So basically like that will make the system to achieve very high performance. And also like this kind of immutability, so we can enable some additional new optimizations, for example like auto tuning or something, because this kind of data or index is not changed, it's static. So that means like like we can leverage some machine learning techniques to do more advanced tuning or something. Yes.
If you're building an index for each segment separately, does the merging of the results from each of those indexes add complexity or difficulty here, or is it relatively simple?
Well, so one thing like well, for the merge, so currently for the single store, like they are using a very naive approach. So they are just, if you want to merge these two segments, we just rebuild a new index for all the vectors in these two segments.
The merging of results when you're asking for results back.
Yeah, merging is very fast because like if you want to search, so basically like you search topic here, you search another topic here, you just merge the two topic results, right? That's very fast.
Okay.
Yeah.
So are you saying that you're searching sequentially through the entire layer? Are you searching in every single segment of?
Oh yes, right. So basically, like if you have multiple segments, then like you have to search like multiple. So basically, like those queries like they are searched like in parallel for all the segments. So later on, like there's a pair bound thread so the background thread will continuously merge different, smaller segments into bigger segments so that we can have better performance. But that kind of merge process is done like in the background thread. So that's very similar to the RocksDB comparison something. So that's very similar.
So I wouldn't be concerned about the merging part of the LSM because that seems to be standard.
Yes.
But when you do a search in an LSM,
yeah,
usually at most one segment from each layer is searched when you do an exact search.
yeah.
But in your case, if you have to search the entire layer,
Yeah.
that essentially means that you're touching the entire data on disk when you do searching.
So basically, well, another benefit here is like we can do search in parallel because like all the segments they are, there's no any overlap, so we can do search in parallel. And also like if there are not so many, updates, there's going to be like just one single segment, unless you have a lot of updates. Right, because all the new updates they are going to be in a new segment. But like if you don't have so many updates, then like you only have one single segment.
And
So
also each segment has its own index.
yes, every segment has its own index, so it's independent of each other. So in practice, that's fine, I would say. Yeah.
Does that mean data only gets added in the console?
Yeah, they are going to be there's no like it's immutable. It's not going to be modified.
So you only ever have to worry about segments getting added.
Yeah, like if you have some new data, you just put it here. If it's full, you just pass it to a new segment. That's it.
Okay.
So those old, segments, they are not going to be modified. Well, like later on, like if you want to do merge, then like you have to merge these two indexes.
That is kind of an interesting question though. In LSM trees, deletions are usually handled via tombstones, right?
Yeah.
And you
Well,
identify them because you kind of search early.
well, here like for the delete, that's something special case. So basically, like we maintain a list of deleted items, and then like we do search, and then once we have the results, we just check. Whether which items they are deleted, we don't return those deleted items. So yeah, for the deletes, that's some special cases. Yeah. Okay. So another unique architectural benefit is something, single store, that's optimized for operational workloads. So basically like those kind of one is about, it supports sequable encoding, sequable encoding. That means like, once we return like a top key vector IDs, if we want to find out the top key actual vectors, we don't have to decompress the entire segment. Like we can directly, go to the right place. So without the decompressing the whole segments, that's something about the sequable encoding. Also, like they support segment elimination. That means that's useful for the filtered vector search because like we can check if this entire segment is not relevant. We don't have to search this entire segment. So this kind of optimizations they are relevant for filtered vector search. Okay. Well, this is a high-level idea architecture. So basically, like that's a distributed vector search system. So there are many leaf nodes, and there's an aggregator. So basically, like once we have a query here, we just so basically like all the entire data they are going to be partitioned in different leaf nodes. And if we have a query, we just send it to multiple leaf nodes, and then like we will combine the results. And also like we support like extended SQL semantics for vector search. Later on, like I will explain. And then like also like we do here like we only do in memory search here like in currently. Well, like later on like we can support like a disk-based search, but not like so for this entire segment index like we just put it everything in memory. Okay. Well, like we do real-time updates and transactional support, and then like we can support many different flexible vector indexes, and then like we can also support hybrid vector search. So that's the high level points, and then like I will go deeper into each point. So the first design is like for the index design because like it's a distributed system. So the entire data is sorted into partitions, and then like every partition includes multiple segments, multiple LSM segments because of updates. If there are some updates, we have multiple, segments. Otherwise, there's only one segment. So like one design decision like we want to make is whether we build a vector index for the entire partition or for every segment. Here like we just do like a per segment index, because this entire partition, this concept is a mutable data set, because like there are some in-memory rules law, and then like there are some new segments that are going to be merged or created or something. So basically like for this partition set, this concept, that's a changing data set, and then like we don't want to do that. We only want to do like build indexes on the immutable segments. So that's why like we build like a per segment index, and then well, like for the in-memory part, like we don't do any indexing because the size is small, as I have said before. So basically like we just do a full vector search, full scan of the vector data. Okay. Well, like the benefits is like they can support updates very efficiently, like using the LSM style. We don't have to directly in place update the existing graph SNSW index or something, because they are pretty slow for the updates. And then like we can leverage existing vector high performance vector index implementations, right? And also like it's pretty friendly to auto tuning, because like the data is static. So we can leverage like machine learning techniques, right? So we don't have to consider workload change or something, right? So yes.
I have a question. So if I understand correctly, the way you then handle deletes is that you have another like metadata that remembers which methods have been deleted.
Yeah.
So then do you ever do some kind of garbage collection, defragmentation?
Yeah. So basically like there's I think so basically like we have a vector index merger. So basically like there's a background thread. So we'll continuously like do the compaction, and then like we'll delete the necessary if those vectors they are deleted, we will remove them from the index.
Answer.
Yeah.
Correct. But my question is, so that makes sense. But my question is then over time we have segments.
Yeah.
And segments have like a bunch of deleted items.
Yeah.
And at some point a segment might have, I don't know, 30% deleted items, depending on the workload.
Yeah.
Do you ever then say, oh, let me take that segment and recompress it?
Yes. So basically like we will like for the deletes, like we will basically like even for the merge, like we will rebuild the index for that particular segment if there are some deletes.
So, and do you do that every time or every so often?
So basically like there's a background thread. That kind of background thread is continuously like monitoring this kind of stuff. That's the background activity. Well, like that depends on
it goes as segment to segment.
Yeah, it goes segment to segment. Yes. Right. So basically like that depends on the resources. We'll basically if possible like we'll continuously monitor those kind of deletes. Yeah. Okay. And then like for the merger, so basically like we'll merge smaller segments into bigger segments, and then like we'll build bigger indexes. Well, currently like one project that we are working on is like how to efficiently merge two graph-based indexes instead of like build a new vector index from scratch for these two new segments. So how to leverage these two existing graph-based indexes and then like to merge directly. So currently like we are working on this one. And also like in terms of the vector indexes, currently like we support both IDF-based index and graph-based indexes. Okay. Well, like later on like currently I know like there are some engineers like they are working on disk. They are working on to support like a disk-based vector indexes. So that's something like that will be supported in the future. Okay. So once we have a vector index, now like we can do vector search using SQL. So you can select something from the table where well for the where that's about the filters. Now like you can do order by limit k. So basically like you only need to return top k results. Okay. For this kind of order by limit, so basically like in terms of the query execution, we do push down operation. So for the push down, like there are two levels of push down. One level push down is about once you have a query here, like we push down the query to the leaf node, and then like for inside the leaf node, so we push down the top key vector search to the table scan. So basically, like for the table scan, like we introduce a new physical operator. So basically, like instead of scanning the entire table, to find out the top key results. So like we have index, top key operator. So it's very similar to the database index scan, right? So we return the top key results. And then like with every leaf node will return top key, and then like for the aggregator, we just merge the results and then return global top key results. Okay, that's the pretty standard. Query execution plan.
Good
Yes.
question. Do you do an approximate search?
Well, so basically, like here, like for the top key, operator, like this is about like approximate search. Yeah. So basically, like every leaf node will return top key results. That kind of top key results, they are approximate, because that will check the that will search the vector index, right? So
And then when you want to sort merge them, then you only keep the top key.
yeah, right. Yeah, because like then like like the similarity of from the query to every item, so you can simply do a merge sort. Okay. Any other questions? Okay, and then like you can also do filtered vector search. So for example, like you can add a where something, a where predicate, and then like if you want to search, for example, like the price of assuming like these vectors, they are about the Amazon online shopping products or something. Then like you can search using some price filters or something. So for the filter vector search, so basically like you want to search the top key, but you also want all the results they satisfy a particular predicate. Okay. Well, there are two types of in terms of the query execution. There are two types of execution plans. One is like you can do pre-filter. Pre-filter, that means like you do filter first, right? Just use a B tree or something to search this filter first. And then like from there, like you can search like what kind of vectors there are. Like they meet the top key results. Or like you can also do like post filter. Post filter, that means like you do filter afterwards. So you will run top key search first, and then like once you have the top key results, then like you can check whether those results they are they can satisfy the filters. Here, like for single store, like we are using like a pre-filter. Well, many systems like they're using pre-filter approach, because that can guarantee that can always, because like the post filter, like they cannot always guarantee the key results, because like after some filter, especially like if the filters if it's very selective, so like you are not going to, sometimes like you may get a 0 result. Okay. And then like if you want to get key results, then like you have to issue multiple filter vector search. That's expensive. So basically like we are like we use pre-filter search. Well, like there are some optimizations, but yes.
So are you going to describe to us the index structure that supports this pre-filter search?
Well, so basically like here, like for this filter, like it's just like a simple B tree structure.
And after that, you do a sequential scan to find the nearest neighbors?
No, like after that, like we do, so basically like we do pre-filter. That means like we use this, we will search the B tree to find out a list of qualified items. So we store those qualified items in a bitmap. And then like we pass this, after that we will do vector search. But then like we will pass this bitmap to the vector search, procedure. And then like during the graph traversal or something during the vector search, once we have a candidate result, we will check whether that result meets the bitmap requirement. And then like if there's a match, we will continue. Otherwise, we will just ignore. So basically, like that's the process. Yes.
So the question here, so does pre-filter this approach always outperform post-filter? Because I would imagine running approximate research way slower than just scanning.
No, it's not always. So consider like for the extreme case. like consider like this kind of filters is now selective. So basically consider like there's no like so all the results like they can meet this I mean this filter, then like the post filter is good. Because in that case like the vector search is very fast. The vector search usually like the vector search is just a few milliseconds. That's very fast. So like it's always good. Then in that case like it's good to do the post filter.
So is there any mechanism in the single store that automatically decides which?
Yeah, I think like we should do that, but currently no. Currently like they always use the pre-filter because like they find out I mean this kind of filter is pretty selective. Well, I think that's something possible like in the future. Yes.
Is there a system that only does post filtering? Because it seems to me like if you are saying limit k and you get less than k result, but there are actually more result, that seems to be a violation of the semantics.
I'm not sure like whether there are systems they only do post filter, but I mean there are systems like they do both. Like they can automatically select between pre-filter or post filter or something. I'm not sure like whether there are systems like they only do post filter. That's something I'm not sure. Yeah. Any other questions? Okay. Well, there are some optimizations, but I can skip this slide. Well, besides the filter vector search, like there are, we can also, we also support, some other advanced vector search, like range search. Range search, that means if you want to find out vectors, like they have a specific, threshold with this particular paravector, you can use this range search. Or like you can do range join, like if you have two sets of vectors, if you want to find out all the matching pairs or something. Or like if you can also do like hybrid vector search with keyword search, and then like you can combine the two scores. But the point is like for those advanced vector search, like we just use some naive implementations. So there are not many. So at least like we haven't done too much optimizations here. So I think like there's a lot of optimization opportunities. Yes.
So for the similar, like for the vector similarity, which distance functions do you use?
So like we are using Euclidean distance.
Okay. And the other question is for the keyword search, do you build a separate inverted index?
Yeah, yes, because like currently like they have already supported the vector keyword search inside the single store. So they have already built inverted index there, so they can compute the using BM25 or something, some score functions there, so they can do some hybrid scoring. Yeah. Any questions? And then like in terms of the experiments, like we compare vector search single store with Mills. That's a highly optimized specialized vector database. And then like as you can see, like for both its SW and IBF index, they're pretty, so the performance is pretty close. And then like so basically like we can achieve comparable performance with Mills. And also like we also compared compared with pgvector. pgvector, that's a very popular vector search library inside the Postgres. Well, so the performance there is now very good. It's still much slower even today. Yesterday like I talked with some Microsoft guys. Like they are working on improving like a pgvector. So the pgvector performance is still slower than specialized vector databases. By several times. Well, here like, especially for I think for updates could be even worse. So basically, like that's something like so basically like for and then next like I will talk something about the I will talk something about the pgvector. But for now, like, any questions so far?
How big was the data?
Yeah, like it's 10 million vectors. I think by default it's 10 million. 10 million. It's not that 10 million probably.
And how many dimensions do you have for your vectors?
Around 100 or 128 or something. Yeah. There are some standard vector data sets. So the largest one, I think it's around 700 or something dimensions. I think that's the largest one.
In this experiment, did you do any inserts, deletes, or was the data static?
So here, like, I mean, for this experiment, it's only about the search. It's not about there's no
So
deletes.
if you're doing just search, then if you have like multiple segments, one segment.
So here, like, I think like for the search, like there's only one segment, because like if you have, I mean, updates, then like it's possible to have multiple segments. Yeah. Okay. And then like I mean, like for the because like Mailbox is also doing like a segment-based vector search. So I mean, we configure the same number of segments, because like Mailbox is also doing this way. They're using LSM-based updates. Okay.
And the segment fits in their memory, I guess.
Yes. That's in memory-based vector search. Yeah, and for disk-based vector search, that's now very mature. So basically, like there are, well, Microsoft has some techniques, but it's still now widely adopted. So mostly it's in memory vector search. Yes.
And so is this single-threaded or multi-threaded?
Multiple, because that's about, I forgot how many threads. It's multiple threads.
Okay.
Well, because here like it's only about the search, so I mean it's pretty. I mean you don't have to do have to do too many logging or something.
So are all the systems multi-threaded? And
Yeah. Yes.
So it is not distributed.
For this one, no, it's not. Well, like in the paper, like we have a section talking about like the scalability in terms of the scalability of the number of nodes, of the number of the data size or something. So, but for the default setting, so it's just the one search.
How many vectors are retrieved per search?
How many vectors? Top K, I think probably like a top 10 or something. So default is 10, I think. Yeah. Okay.
So one query returns 10 vectors.
Yeah, 10 vectors. Yeah.
Do
Can I ask a question over the Zoom link?
Yeah. Okay.
How many vectors can you actually support from memory? Like if you're serving your search from memory?
How many? Can I say it again?
How many vectors can you actually serve from memory? As in, suppose, how large can your vector database be if you're
Yeah, the total size. I think like in this experiment, I think we are using 10 million vectors. So 10 million vectors. Well, like it's purely like in memory. It's purely in memory. So here, like we don't. I mean, like we haven't supported the disk-based vector search. So all the, I mean, vector data and the vector indexes, they are all in memory.
okay, and these are flat vectors, right?
Yes. And also like for the mailbox, like that's also like in memory. That's also in memory. I mean, database.
Got it. And for the joins, are you doing any specialized optimizations, because you want
that's
all kinds of joins to work with vector search, right? Because it can lead to repeated vector search.
Well, like so basically, like for the join, like it's basically like a full, I mean, nested loop join. It's so like we don't, I mean, like we didn't do too many, I mean, optimizations. So we just use the, I mean, I would say like a straightforward implementation. So that's why, like I think, like there are some research opportunities here for the advanced vector search.
I agree. There's a lot of stuff that can be done in this.
Yeah. Okay. Any other questions?
Yeah, I have a small question.
Yeah.
Do you know why the PG vector is that slow?
Yeah, so yeah, I will explain like next. Yeah. Okay.
I don't know, but how much does the performance change when you change K?
I don't think it will change too much. I'm not sure, but I mean, I don't think that will change. I mean, too much. I mean, if you from K, if you change from 10 to 20, I mean, I'm definitely like it's not going to be doubled, because I mean you still have to pay. I mean the traversal or something, so it's not going to be doubled.
So you traverse the entire data anyway.
Yeah. Anyway. Yeah.
So just the buffer that.
Yeah.
Okay.
Okay.
Just curious.
Okay, and then like for PG vector for Postgres, we have also done some investigation to understand why, I mean, PG vector is slow, and then like so Well, actually, like we have started like this investigation started in 2022, but in 2022 at that time like PG vector was very slow. So like PG vector was now popular. There's another system called PIS. PIS that's designed by Alibaba. So basically like that system, we found out that system is faster than PG vector. But like PIS is also slower than Mills. So basically, like we investigate, PIS. We are using like a PIS for the platform, and then like we find out why, because like PIS is also implemented inside the PostgreSQL. So we want to find out why PIS is slower than Mills. So we find out, there are some architectural issues of PostgreSQL, and also like there are some implementation issues of Postgres that can lead to the low performance. So basically, like last year, like we published a paper like to understand whether there are some fundamental limitations in supporting vector search in PostgreSQL. Well, like although like it's published in 2024, so basically like we started this project like in 2022. And then like so the architecture of PG vector or PIS is something like this. There's some new indexes extended. So you have to extend some index to support vector search. And then like in order to support vector search in Postgres, then like you have to follow some requirements, some rules in Postgres. So for example, like you have to implement some interfaces, and then like you have to design the index structure to be aligned with the page-based structure, because like Postgres that's a disk-based system. So like they have then all the pages they are designed to be, they are using like a slotted page structure or something. So basically like you have to map your in-memory structure to the disk-based design. Otherwise like that's not recognizable by the SQL optimizer. So basically like that will create some overhead. So especially like we find out there are some reasons why Postgres is now very good to support vector search. One is that it does not use native vector index implementation. Native vector implementation, because like all the indexes implemented in Postgres, like they have to follow PostgreSQL, the index page structure, and also like they have to implement certain interfaces or something. So I think like especially for the first one, because like all the currently for all the mostly for the vector indexes they are designed in memory, but in order to be implemented inside the Postgres, you have to convert the in-memory structure. You have to manually convert the in-memory structure to the disk-based one. So here like, there's an example here. So here this is the standard IDF the quantization-based or partition-based vector index. That's in memory. Now like you have to map this index to disk-based structure. So basically like you have to convert all those centroids into centroid pages. Those kind of clusters into cluster pages or something. Even though those kind of indexes they are not designed to be disk-based, you still have to do that. So that will, I think like that will introduce a lot of overhead. And also like Postgres, that's a disk-based system. Even if like we store everything in memory, there will still be some overhead in the buffer manager, some page-oriented like indirection or something. So those kind of overhead is also pretty huge. And also like in terms of the updates, because Postgres is using a B-tree-based storage engine, but for Mills it's based on LSM-based storage engine. So basically, in terms of the updates, there will also be some performance gap. So as a result, so basically now like so the PG vector, so the performance is now very good. So the question is like how to improve the performance for PG vector. So one way is like we can follow single store architectural design, but that will require too much result for Postgres. But here like we observe that the performance, so vector search heavily relies on vector indexing. So if we can decouple the vector index from the table data, although like original table data is maintained like using B-tree-based storage engine, that's fine. As long as the vector index is maintained separately, that will lead to high performance because like we can manage vector index like separately. Once we decouple vector index from the table data, then like we can do whatever like specialized vector databases are doing, and then like we can achieve high performance. So that's something like we are working on now. Like we will leverage the lessons to build a single store, and like we will, decouple vector indexing and then make it, as a service. So that's something like we are working on. Okay. So another one, something like we are working on is like how to support vector search in cloud native Postgres, because for example, like for Amazon Aurora or something, if those systems like they are deployed in the cloud, they are separated, they are disaggregated. So this kind of the disaggregated nature, I will pose some new challenges to vector search. So that's something like we are thinking. Okay, so running out of time.
About 7-8 minutes.
Okay, then I think I will skip. This part I will go directly to the last part. Okay. Well, for this part, so basically, like we build a vector search inside the graph database. Like we call it like a single that's the entire graph, but it's basically like that can be implemented in any graph database. Okay. So the point is like we want to support both graph rag, if you know like something about the graph rag versus vector rag. So basically like we want to combine both. Okay. Well, like I will skip all the details and then for the last piece. So basically like I'm thinking like something beyond the vector databases. So the point is like we want to, so eventually like we want to support large language models over any type of data, not just about vector data or text data or something. So we want to support if possible, like if we can support any large language LLM query over any data, especially for untrained data, unseen data, for example, some new data, some enterprise data, or some domain specific data, that's very good. So in that case, like the role databases will play a very important role in this ecosystem. So basically, like we can use databases, as a retrieval engine, and then like we store all the relevant, information here. And then once we have a query here, we can convert, we can search the database system, and then like to find out some relevant results, and then like we can send those results to a large language model. That'll be very, very good. So that means like this kind of database has to be a multi-model database. So that means like currently like I'm thinking we can support like relational data, vector data, text data, JSON data, spatial data, and graph data. Well, it's possible to be, well, we haven't considered like for example images, videos, that's also possible. But the point is like we want to, for this kind of multi-model database, like we want to achieve, one is we want to achieve comparable performance with specialized data systems. Well, currently, although there are a few multi-model databases, they cannot achieve comparable performance with their specialized data systems. There's still a huge performance gap. That's something like we want to bridge. And also like we want to support cross-model query processing very, very efficiently. Well, also like we want to support, natural language queries because, that's the requirement for RAG. Also, like if possible, we can support multiple large language models, so we can automatically select based on what kind of queries. So so that we can reduce cost. So the architecture could be something like this. So for example, like if I want to find out some products from Amazon online shopping or something, then you can specify your requirements using a natural language, and then like that kind of natural language will be translated to an extended SQL query, because that means like we are going to extend the SQL semantics to support multiple types of data. And then like for the query optimization layer, so that's basically a hybrid query processing optimization problem. For the storage layer, so basically like we can support both structured data and unstructured data and different types of indexes. Okay, and then like that's basically like a multi-model database. And then like once we have the results here, then like we can send those results to different large language models. And then like to find, we can automatically tune which one we want to send the results to. Okay. So that's all. So basically, so thank you. Any questions?
Yeah, so before that, can you stop the recording?